So we're going to talk about free energy today, and we're going to do that from the perspective of the entropy. So the change in the entropy of the universe is equal to the change in the entropy of the system plus the change in the entropy of the surroundings. Under spontaneous conditions, this is greater than zero. So delta S of the universe is increasing for a spontaneous process. For an equilibrium process, this is equal to zero. So if you have a dead battery, you've reached entropic, or you've reached an equilibrium, therefore delta S of the universe is no longer increasing, it is going to be zero. So we have a problem with using this approach. That problem is that the calculation of delta S of the surroundings requires precise knowledge of the thermodynamic surroundings. That's hard. So if you have your system and then you have your surroundings, so knowing how heat is leaving that system per temperature, so the change in heat per temperature is going to be the definition of your entropy. So ds surroundings is equal to dq of a reversible process of the surroundings per temperature. So at constant pressure, this becomes dH of the surroundings per temperature at constant P. But that's under constant pressure conditions. If you don't have constant pressure conditions, then you can't make that jump, which makes this dq reversible that much more difficult to determine. And so being able to make or to construct your thermodynamic surroundings such that you know which thermodynamic potential you can put in is a huge step. Cool. So that's hard to do, and we can't just snap our fingers and all of a sudden we do that. So what we're going to do is we're going to explore this relationship and come up with an alternative approach to quantifying whether or not a system's process is spontaneous or not. Okay, so now I've just rewritten. So now we have ds of the surroundings, let's just say surroundings, is equal to dH of the surroundings per temperature. So and this, again, this is constraining it to be a constant pressure system. So what we're going to do is we are going to look at what happens at constant temperature. So at constant T, delta, well, I should say, we're going to integrate this, and then at constant temperature, that means that this temperature can come out of the integrand, and we're left with delta S surroundings is equal to 1 over T integral dH surroundings. Well, that's lovely, because that just becomes is equal to delta H surroundings over T. Okay, so we're going to start with this and then explore. And we need a first law of thermo to explore this. So delta H of, so how do I have my universe is equal to delta H of my system plus delta H of my surroundings. Okay, so based off the first law, this is going to be equal to 0 under constant temperature conditions. Okay, so then what we can say is that delta H of my surroundings is equal to a minus delta H of my system. I'm sorry, I said that was a constant temperature. That's not true. This is just the total enthalpy of of an isolated system is 0. Sorry about that. So because I have delta H of surroundings is equal to minus delta H of my system, I can now put this into this relationship for delta S of the surroundings, because remember the problem. Delta S of the surroundings is very hard to determine. So delta S surroundings is equal to minus delta H of my system divided by T. Everyone happy with that? Cool. Okay, so I'm going to plug this back in. So I've got delta S of my surroundings. I'm going to plug this now into my relationship for delta S of my universe. So this equals delta S of my system minus delta H of my system divided by T. Okay, so I want to clarify this a little bit more. I've got this inverse temperature on the right-hand side under my delta H of my system. So what I'm going to do is I'm going to now multiply this whole thing by T, and you'll see why in a second. So this becomes T delta S universe is equal to T times delta S of my system minus delta H of my system. Okay, so the other thing I'm going to do now is I'm going to emphasize that here on the right-hand side, I have everything in terms of my system. I don't have to define my surroundings at all, which is awesome, but I've also got this negative sign, so that's a little tricky. So what I'm going to do is I'm going to rearrange this algebraically just to make it a little cleaner. So I'm going to say that minus T delta S of my universe is equal to delta H of my system minus T delta S of my system. Go team. Okay, I'm hoping this is looking familiar. So now here I've got two thermodynamic potentials, this one and this one, representing my system. I now have this criterion to where I can say that I'm going to now define the Gibbs free energy equals minus T delta S of my universe. And so this then becomes the criterion for spontaneity of the right-hand side of the equation of the system. So this contains all the quantities associated with my system, and this defines criterion for spontaneity. Go team. So I've got T delta S of the universe with a negative sign is equal to delta G, which is equal to delta H minus T delta S. And for a spontaneous system, my delta S of the universe is greater than 0, which means my delta G needs to be less than 0. So delta G is negative for a spontaneous process. Delta G is equal to 0 for an equilibrium process, just like delta S of the universe is 0. And likewise, delta G is going to be increasing, whereas delta S of the universe is negative for a non-spontaneous process. And that all originates from this negative sign right here. So this is for constant pressure conditions. If we have constant volume conditions, and we start with the delta S is going to be related to our delta internal energy per temperature. If we do that, which again, under constant volume conditions, we get what's called the Helmholtz energy. And that's represented by A. And so, oh, sorry, this should be delta H. There we go. Whew. So I've got delta A is equal to delta U minus T delta S, where U is the internal energy. And so this Helmholtz energy, again, will have the same conditions associated with spontaneity. And so delta A will be less than 0 if delta S of the universe is going to be greater than 0. So you can say that delta A is equal to minus T delta S of the universe, again, under constant volume conditions. And that's, again, the reason that we're using U instead of H. Go team.